1, 2, 3, 4, 5. Is it working or not? Okay, 1, 2, 3. Okay, 1, 2, 3. Okay, everything works. So, dear ladies and gentlemen, that's the second stream of the week. That was the idea before, to do 2 streams per week about articles. Maybe I will scale to 3 streams per week because I feel more confident in the articles. Not because my app became better, but just because if you do it week after week, you just get more skills and you get more familiar, become more familiar with the topics. So it's slightly easier for me. So yesterday I was thinking whole day about the article, which I'm going to discuss today. And today, half day, I was rested in doing some other things, and recently I have finished understanding to some extent this article. And that means that I'm ready to stream, and after it I will consider this article fully analyzed to a decent extent. So I will not be focusing on it unless I really need it. And the second thing I wanted to say is that I'm very happy that number of subscribers is growing. Now there are more than 250 subscribers, which is a really great achievement. I hope that they will once see some videos. I'm not sure if they're really active, but it looks like a great achievement, and let me pretend that it's indeed a great achievement. I mean, it would be better if they were active subscribers who were liking videos and watching my streams, at least, I don't know, scroll through them to get some impression of what happens during the stream. Maybe they will do it later, I don't know, but maybe no. And last thing which I wanted to tell in scope of the preface is that this article is the most experimental article which I have ever read actually in my life, and definitely which I have streamed. So that's the first article which I couldn't read just like on my own and like fix some questions. No, there were a lot of sentences which I didn't understand at all. So I'm reading, I have no idea what is meant, partially because of very academic language, which wasn't familiar to me. And second reason is because it was very experimental article. It is very experimental article, and I'm not still that familiar with experimental part of the topic that I'm streaming about right now. But next experimental article should be way easier than this one. Yeah, so in order to prepare, I little bit shifted away from my typical framework. Usually I read and don't speak much with AI, and then I speak with AI before the stream. But with this article, it was nearly impossible to understand it without AI. And that's why I was reading and discussing with AI, and only then I asked, like, do you understand general everything fine? And GPT said that yes. That means that, well, I think I still understand something. So, okay, let's then jump finally to discussion. Maybe someone will write some question finally today during the stream, but I'm not sure. Usually no one asks me anything, which is absolutely fine. Did something fall? No. Okay. Technical distortions. So that's the article. The electric insulator states in 1T tantalum disulfide. Let's check the citations. It has 37 citations right now, and it's 2026, so during 4 years, which is not little, not a big number. And we can see that really a lot of people were working on this article. I guess the majority of them are from China. Yeah, so these are people from China. So what is the motivation for this article? Basically the same as for the previous article from the previous stream, that like what happens with tantalum disulfide right now. Yeah, if you want to do good research, we need to know what happens, what people write about, what they have researched, and which questions they ask. And here there is the research of some layered properties. That's the continuation of the discussion from the previous stream. Yeah, and by the way, in the scope of preface, I should say that how much time did it take? Basically, it took me 1 day to prepare this article, but during the first day I was slightly distracted to other activities, and during second half of a day I was nearly doing nothing. So if I combine all the time, it took me just 1 day. But totally it will take me 2 days, because half of second day I was basically resting and doing things related to my life, and now I will be streaming for several hours. Then I will spend some little time on thinking about the questions that I think about, that I write during the stream. So totally one article takes me right now 2 days, and that's like 9-page article, but some pages are for literature. So purely there are how many? Let's check. There are 7 pages of the text. So 7 pages is the amount of information which takes me 2 days to really understand. But this article was way harder than the previous one, because, as I said, that's about the experimental part. Okay, so the motivation is that I try to understand what is currently happening in this direction of these materials, and some theoretical results, I guess, are published so like each month, and experiments are done each month also. And right now we see approximately known paper, because like around 40 citations, it's not a little thing. And they are telling us about some bulk properties. So that's what we're going to discuss right now. I just wanted to show you the original article before we go to the focus structure 2. And here is my article after my analysis. So let's start with extracting some useful results, because that's the most important thing. And then we will, as usual, go to the discussion of each sentence. So unfortunately, it's a little bit hard for me to extract key results, because, yes, as you know, I was reading it only 1 day totally. And okay, so the main idea actually maybe is written here, that okay, we have this material. The question is that so it has some gap. It's an insulator at low temperatures. And the question is that are insulating properties arise from the layered how to say structure, like interlayer interaction, or from the like one layer itself. So if you have one layer, then you have just two-dimensional model, and that's the Mott's model, as we heard several times from the previous streams. But if we have a layer interaction, then I actually have no idea what the formula is for this model. But yesterday I tried to look for this model, like speak with ChatGPT, but I didn't get some really good answer. There was like some cited papers, there were cited papers, and I saw one formula, but it's not telling me how exactly they see the interlay interaction. So that's why it's hard right now for me to summarize what's the was the conclusion of the paper, because yeah, there are experiments which we will go through soon. There are some statements about two types of insulating properties, and basically it's not written in the article much, but in the title it's written dualistic insulator states. So that's the main idea of this research, which is reflected in the title, that this material has insulating states, and they have two types of nature. I mean, two origins. One type is the interlayer interaction, another type is the interaction just in one layer. And basically they say that sometimes the interlayer interaction dominates, sometimes the interaction scope of one layer dominates. Okay, so I have learned right now a question which I wasn't asking myself, but that's an important question. So yeah, so I wrote this question for myself for later thinking, or at least for plugging to ChatGPT. But regardless of the fact that I can't really extract after one day of total thinking about this article, so I can't extract what is the real conclusion. At least what I really understand is that they really tried to figure out how important this interlayer interaction is, and they did a very complicated experiment and also a complicated simulation that we will go through. And the main idea, that's what, like, why I was writing this question, because I wasn't sure what is the main idea and what is the main conclusion. But maybe we will learn it during reading of this article, because it's somewhere there, as you can see by the comments. I was thinking about it, so it should be there also in my head, but I can't right now extract it to you. Oh no, there's another article already. So, okay, so how should I summarize this article in a proper way? That they tried to understand what is the nature of the dielectric property, and they did a lot of experiments actually to measure some distances between layers. So idea was that what if we just move layers slightly, one corresponding to another, like shift, do the shift and calculate. Yeah, like it's really not clear why this shift is related to some insulating properties, but we will see it during the article. But somehow, by this shift of layers, they tried to teach us what is the real nature of insulating properties of this material. That's maybe the main conclusion, and I mean the main thing that is written in the article. And the second main thing is that, like, there are a lot of experimental results, and maybe that's the first article which has the results for this slightly shifted configuration. So before there was this stacking, or like very shifted stacking, but actually while reading this article I learned that there are so many articles about similar topics. So thinking about maybe to make the challenge like 30 articles per month, like one article per day, to stream them and discuss them, because they are very similar, so it's very easy to do it if you have like experience for, I don't know, just 1 month of streaming. But okay, I'm not sure what is done, what is not done here. We are presented with results, and maybe they are the first results ever. So we will discuss this maybe in an hour, maybe later, I don't know. So we have spectra of this shifted configuration. We have some other experiments which I forgot because I wasn't doing experimental part. It's like scanning tunneling spectroscopy, as far as I remember, like derivative of a current, and X-ray some things, and we will discuss it later. So maybe that's the main value of this article, that these are the experimental results. There are, of course, the calculations, and that's the image that I chose for the covering of this stream, because it shows basically two staking, how they call it, but these are basically configurations. So the first configuration, the second configuration, they measure experimentally them, and here are the results for experimental measurement, and that's the results for theoretical measurement. And maybe they actually coincide somehow, but that's what I wrote already here. Did they fully reproduce their calculations or not? No, so I'm not sure. But like, what is the advantage of this app is that it allows to use AI with the comfort way. So later I'll just plug this question to ChatGPT. He will give me something, and there is from 20 to 60% probability that he will give me some useful information. So yeah, I will understand it later. And for now, that's the main conclusion of this article, that these are different configurations. And these are results for different configurations, and the results of theoretical calculations are also presented without, of course, any formulas, because they did just numerical computations. So maybe it's a good idea to learn the cited papers to learn how to reproduce these computations. But again, right now we can try to plug to ChatGPT, and maybe already this would be enough for reproduction of the results. Otherwise, it would take really way more time for me to do it. So, okay. So let's, after my attempt of explanation of essence of this article, let's try to read it line by line and understand what's going on here. But before, I'll add some water. Okay, so here I will, like, during this stream, I will try to be faster, because like streams for 4 hours, it's a nice thing, but why not to do it in 2 hours if I can do it in 2 hours? So let me try to do it. So, okay, as usual, like, yeah, let's start with the overview of the structure. So what this article is, it's the introduction, which we'll go through right now, then a lot of results, then a little discussion. I'm not sure what is in discussion. I already forgot. Maybe some future like directions that, hey, actually you can do that or this later. But yeah, okay, that's also a really good question, which I should add also here. Yeah. But basically, this is a very short part. This is the big part, but there are different kinds of results. So each type of result is not that, it's not a very big section. So that's the overview of today's plan of this article. And I have some also questions, comments, but these are not really important. So let's put this image here and start article with, of course, introduction, which is something like this. That's the only introduction. So little, actually. Let's just check if I didn't miss. Yeah, so as you can see, that's exactly the introduction. Just was surprised that it's so short, and yeah, but that's the original introduction. Okay, let's try to do it way faster than in previous stream. And by the way, if you have some questions, you can write them. No one has been ever writing them, but still, the idea is that actually it's possible to have some interactions and nice discussions. Okay. Okay, so the first sentence tells us what I have already told you, that there is this question about layered and bulk properties. So we know what happens in layer property, layer material, and now we're not sure what happens in the bulk. And that's why we have this article. Okay, let me just write the question for myself to... Yeah, okay, I'll double check it because I was thinking about it and I forgot. I mean, I was even trying to check it, but I forgot the conclusion. So what is known? Because all the previous streams we were discussing like layered materials, like one layer, but it was not really explicitly written that is it like top layer of a bulk material or it's a selected layer. So that's what I wrote the reminder for myself to check it, because that's the first paper out of all that I have streamed about, which exactly points out the difference between layer and bulk. And if we look at this result, it's important to understand what was before. Was it a layer or the bulk sample? And I'm not sure, maybe we have already learned a lot about just one layer material. And here it's written that if we have a bulk, then it's not really clear what happens. And that's the introduction to this study. And they will tell us how to describe the layered material. Well, yes, they will tell us something, but it's not actually true, because they will say like, hey, we just did DFT, and they describe their method. I mean, they give citations for their method, they name them. So that's the main thing that you can learn about the description of such layered material, but not so much theory was presented here. That's why I have already written the question, what is the real conclusion of this article? I'm still not sure, unfortunately. But here it's written that it will teach us about the description of layered materials. And it's written that if we have layered materials, then it can give us insulating state. And it's written that there is a dualistic nature. So as I was explaining before, I mean, it's not really written here, but the idea is that there are these two types of insulating properties, and it could be a layered insulator because of some interlayer interactions, and insulator because of interactions in scope of one layer. So this is the very important statement in scope of the very important takeaway of this article, that actually we have both properties. And yeah, sometimes one reason for insulating is there, sometimes another nature is there. And that's the sentence from the abstract. And the last sentence, yeah, so the last sentence is a promise, like vague promise, that maybe you can get something useful from this. And as I was saying several times already during these several minutes, that it's not clear what they really want to do with this theory or with these results. So that's how I summarized this sentence, that maybe you can get something useful, but maybe no, we don't know what useful we can get. But even producing these experimental results and these theoretical DFT calculations, which you can see here, for example, it's already a big step. But this last sentence of abstract gives us slightly, like a little hope to try to use this theory or this result somewhere. And of course, it's not clear where we can use it. Okay, that's the abstract. Now there is the introduction. And the introduction, of course, repeats a lot of things that I have been streaming about during a lot of streams before. So maybe it should be way faster today. So here, this is the first just motivation that, yes, we have Mott insulating states, and they are well known, of course. There are some ideas of applications, and I have no idea why they really can be applied, but of course we have some citations. And what is interesting here is that even in quantum computing, it can be used. And I have no idea why and how, but it's not really important part of the article. Just it's very unusual statement that I have found here in the first sentence. Then were written that people studied a lot the states because it has a lot of properties like charge density wave, which we have discussed previously a lot, superconductivity also, so you can remember this well-known phase diagram. Let me show you in another window, focus structure tool. So that's the well-known phase diagram. So maybe we'll come to this diagram also later. But for now, let's switch to this window. And the previous plot that you have just seen is just the one that's always assumed when people think about this material, tantalum disulfide. But as you can see from this paper, it's already, I mean, we should understand what exactly is meant here, because here I actually even didn't point much attention. Is it like a layer material or a bulk material? But my guess is that's just the one layer. So if we have a bulk, then we need to know more about this phase diagram. And I haven't read yet this article about the bulk material. But okay, I have written already this question. Just let me write this. Yeah, like this. Yeah, I'll just ask it, clever AI, and he will help me. I think it's not a problem at all right now. So, yeah, so this sentence tells us that some people studied this, and we already know it from the previous streams. There are different effects. That's why this material is popular. And yes, in one layer, what do we have? We have this modulation, which is also drawn here. So atoms are not homogeneously distributed, but they are arranged into clusters, which are called David stars, and they are drawn here. And the electrons, which are also there in the material, they are distributed also with modulation, and this modulation is called charge density wave. Of course, there is a polaronic theory, but for this article, it's better not to even post this question about polaronic description. And yeah, and let me check what did I write here. Yeah, so if there is no no layer structure, then there is just one layer, so we can apply Mott-Hubbard model. And right now it's not really important what this model is, but you can check previous streams about this model where it was discussed in more detail. But this special model can be applicable if we have one layer, and this model predicts an insulating state because of like repulsion of electrons, which is there in the model. And that's what is written here. And here, next sentence tells us that something was researched. Basically, it's not clear what do they mean, but that's the introduction. So nothing is. It's like typical thing that we can expect from introduction, that something was researched, but later we'll learn what. And the next sentence tells us that like in the basis of all of these studies, there is the configuration of atomic lattices, and that's what we also see here in this little image, that these layers can be aligned differently, and that's So a reminder that these clusters are called stars of David's because someone long time ago measured how exactly these atomic shifts are, and that's why all people know this community that they are arranged into Star of David. And that's the introduction to this different alignment. So it can be aligned like, let's say, like periodically without some special non-periodic shift, or with some shift, for example, that will be studied later. Here is just introduction of different alignment. And here, okay, that's the part that I never understood during the reading, that we have actually two types of properties. One property is the property in scope of one layer, and another property is like out of plane property, like perpendicular to layers. And that's how world is created, that it's like, let's say, not inhomogeneous, non-isotropic. Like this material has non-isotropic properties because in different directions there are different properties. And here it's written that like if we go even if we look even not in the plane but perpendicular to plane, then we'll still have some insulating properties. And it's written that some theory was predicted a metallic state, and I don't know this theory. That's why this question is here. There is no sense to dig deeper because, like, it's not really important. All the sentence is not really important. But I mean, from theoretical side, yeah, it's interesting to see the theory that predicts some metallic behavior along the perpendicular direction. But from the point of view to get the essence of this paper, we can stop on just level of understanding that it's just insulating, and that's all. But the conclusion is that people were really concerned about this direction. It measured several things. I don't know. Actually, we will look later on, for example, I guess this plot. Is it this A, B, C? Yeah, maybe. Yeah, maybe that's the plot. Unfortunately, the quality of image is not that big, but that's the announcement of the last part of the paper. There will be this resistivity, and it will be in different directions. So even this paper was like, authors from these papers were measuring some anisotropic properties. Okay, and just right now I learned that this sentence is really about, for example, this plot, because, like, yeah, if we look at the perpendicular direction, this one, then we still have a big resistivity. So that's the insulating property that is announced here. And here it's written that in bulk something is not clear, and maybe that's the end of the introduction. No, it's not the end of introduction. Okay, so let's think what's written here. So again, we have a lot of citations. Here are citations, here are citations, and here are citations. So it's just an overview of the bulk properties, and something is not explained there. And also some predictions were done, something was not confirmed. And as was written before, people were not sure about the real insulating mechanism. And I'm not sure if after reading this paper, these authors will be more assured or not about the real insulating mechanism. Because basically the answer is that actually two mechanisms are applicable. If you have layers, you need to apply mechanism of interlayer coupling. And if you have like one layer, then you will just work with one layer and you will be happy. So that's the idea of this sentence. So people are not sure about the real mechanism, but after reading this paper, I'm still not sure about the real mechanism. And basically in scope of theory, they just say, hey, we have DFT calculations, which are giving us something. And that's why I wrote this question, actually. Did they fully reproduce their calculations with their calculations experiments? Because yes, there are no, that's purely theoretical plots. So you see, like this announcement of what's going on to be later. This is the experiment. This is the theory. Who will be comparing this? I don't know. Maybe some very like enthusiastic reader. Maybe I missed something, but that's what I understand after one day of thinking about this article. That this is the experiment. This is the theory. There are some similar features. I mean, the results of the theory of numerical calculations, which is not really the theory, but still like theoretical attempt to calculate it. And yeah, there are some similar features, but it's not really clear if it confirms the experiment or not fully. I mean, to some extent, definitely it confirms, but what about the full confirmation? So that's the announcement of the discussion like later, but for now, let's put this first image here and just continue reading. So announcement here is that what is the real insulating mechanism? Yeah, that's the thing that some people think about. And that's the image that maybe we will go through later because it coincides with the text somewhere here, and this text will give us a lot of links to this image. So let's slightly zoom in, put it here, and read the text. So yes, of course, obviously, if we increase layers, like for example, here, that's the image of layers, then the influence will be bigger to all of the properties. Okay, so here there is the link to experiment of ferroelectricity, and I have absolutely no idea what this experiment is, and this experiment here is written just in scope of the motivation. So still, why are we doing this? You may ask this question. And I don't know, really. I have no idea. Actually, I'm regretting that I was reading this article because it looks not so applicable for me. I mean, that's a great work, of course, big step forward for science, but I need to get some like good starting point for my own research, and I have no idea what to do with this theory. But here in this sentence, they give extra motivation why they are doing this at all, because there is some experiment, actually not one, but four experiments. Oh no, 5 experiments with some sliding ferroelectricity. So I guess based on the title that people were also sliding layers and got some ferroelectricity. And here in this article, that's just another motivation to study these sliding effects. That's the only thing that I can extract from this sentence. And yeah, that motivates us think about again interaction of layers. So I think this format of fast like summarizing is way better than format of trying to think about the sentences, because the value of the sentences is not that big. So if I try to think deeper, it will not really give something useful for me and also for viewers. So I think I will a little bit update my format and will be not reading sentence by sentence during the stream, and that's how it can be twice faster. Okay, maybe not twice, but at least 1.5 times faster. So that's announcement of what will be later during this whole article, that they will shift slightly layers and see what happens, and they promise that they will give us something useful. Yeah, and here there is introduction to whole this discussion throughout this article, that like if we have interlayer coupling, then it should be a 3D band insulator. What is, yeah, like, okay, I just think about that, should I write this question or not? So you might think like two-dimensional Mott insulator, it's like, yeah, what is the difference between three-dimensional band insulator and two-dimensional Mott insulator? Okay, let me write it like this. The question like this: what is? So I can just remind you from the previous streams that if we speak about the Mott insulator, then we should imagine actually something like this. For example, that's the model, so everything is clear. We have one layer. Actually, it's not really one layer. Yeah, okay, just got another question. Yeah, I mean, there is one paper which was telling me that actually this material is not really two-dimensional, it's like three-dimensional or something more, and later this idea was fully forgotten. But okay, that's why I wrote this question. But that's the well-known one model, and here we have another model, so I'm not sure how they are connected, but to understand how they are connected, I need to understand what this model is in general. And we have just DFT, we're not given some formulas. So in order to understand how this shift happens to this shift, I need to understand this model. And to do this, I need to only to read cited papers. And then again, we have this announcement of dualistic nature, which is about basically two properties, two insulating mechanisms. One is the three-dimensional band insulator, another is dimensional Mott insulator. So that's the announcement of it. Okay, but actually, that's a good question. Yeah, okay, I'll figure out this connection later. And the last sentence in the introduction is telling you that maybe it's applicable to other materials. Maybe no, but you can hope that it is. Okay, we have finished introduction. Now the section of the results. Yeah, so here we start with the name of the device that gives us the image of the atoms. That's the name of the device. Then there is a complicated sentence in terms of academic language. And it means that we actually have same layers of well-known structure in scope of one layer, but they are stacked differently, and that's what we're going to deal with. So we can see these images here in the figures. Actually, there is this notation which wasn't explained because it's rather well known, the notation of directions. But yeah, okay, that's the check on thing. Yeah. So here we're given also like some labels for vectors, but I'm not sure if it's really important. I'm just little bit confused that there is this BD here, and later there will be like AB vector and little C vector. But maybe it's not really important. Okay, so we have one layer. In scope of one layer, we have several vectors that connect different atoms. Yeah, and that's basically what's written maybe here. There are these directions. There are these images which were obtained by this device. So clever people who were doing the experiment, they like measured it, and we're just looking at the results. So these are nanometer objects. And we see that there are like there is a periodicity in plane, and yeah, if we have this symmetric stacking, then also perpendicular to plane, and that's what's written here. Yeah, so if you want to see how this is perpendicular, then you can see supplementary figure, but I haven't done this. And also it's not really important about this notation with vectors. I haven't understood it, but that's not really important to understand how exactly this direction is related to some real vector. I mean, maybe that's exactly this vector along this direction, but you might ask what is the 1, 2 bar, 0. And the best thing I know is that this 2 bar is -2. And the whole this notation I have already forgotten, unfortunately. And that's just a reminder for me that later, if I need this, I will return to this. And now we can look at the perpendicular direction. And in the perpendicular direction, there is a slight shift, as is drawn here. And this corresponds to translation of 0.15 nanometers. Okay, just an image of a shift. Yeah. And okay, there is another direction which also has this periodicity. And if we look at this image, then maybe it's along the horizontal direction. So one is the vertical shift, another is the horizontal shift. I mean, no. It should be just two horizontal shifts. Like, yes, that's one direction. That's another direction. Yeah, so these are two shifts are there in the horizontal directions, and they are 4-layer periodic. Yeah, that's what's written here. And now we have a definition which will be very used later. So this shifted configuration is called LC stacking. Yes. Why LC? Because it's laddering configuration. So if we go from layer to layer, it increases slightly, and that's what also drawn and seen from the device here. Okay, now there is this 1C. So yeah, there is some good idea behind this C and F figures, and maybe that's a like very advanced method of how to measure the distances. It's called X-ray diffraction. So if you want to, maybe the important statement is that if you want to measure the distances, you can use this diffraction method, and it will give you some peaks, and from peaks you can determine some distances. So advanced basic understanding of this experimental device is needed to understand how this conclusion is obtained. But regardless of this, we can just see that there is this shift, I guess, between layers. Maybe that's the vertical layer. Like interlayer spacing. That's what I also said, like vertical direction. So this is the result by this mechanism. This, experimental method. Why there is spacing and shift. Yeah, that's an important statement. So maybe not that important, but at least I understand it. So yeah, so this is the spacing and this is the shift. So if planes are shifted, then spacing, spacing is bigger. If they are shifted, then spacing is smaller. If they're not shifted, then spacing is bigger. Yes, that's what's written here. Some peaks, which has a shoulder. What is this shoulder? So, okay, as you have noticed, I'm not expert in these topics, but if we look at these results, then you can see maybe somewhere there a shoulder on the plot, somewhere here, but I don't see it. Maybe that's this, I don't know really. Maybe that's this slight, like little peak, I don't know. Maybe that's what meant here. But I don't think that it's an important statement. Yeah, and the last, so okay, as you can see, no conclusion is here about this shoulder. Maybe you can check it with AI, but I don't see anything important about this feature of the obtained result. Maybe that's about just this very tiny feature. And the last sentence tells us that this configuration is more stable than this configuration. That's why it's hard to get system to this state, and that's why it's surprising for me that they did it. I don't know how. I was reading this in methods section. We'll go also through them, but somehow in a very complicated way they got these results. This configuration which they were measuring, because system tends to go to this state. Okay. Now they will use X-ray diffraction. Yes, again. But now they want to understand how their configuration influences David stars. And we need to look at this now, image 1F. So it again requires some knowledge of X-ray diffraction, because here there are two type of plots. That's the plot of momentum, that's the plot of angle, and I guess like this is the same device, but different parts of it, like different type of data is obtained. And this is the plot of first data, this is the plot of second data. And here that's written that this is the result, 00L index diffraction peaks. Also available in the supplementary figure, but I have no idea what's going on here. We just are presented with these results. And somehow, if we have a Davis-Stars configurations, then we have peaks in this X-ray diffraction plots. So maybe, yeah, so that's exactly the question that's written here, that it's very not clear how Davis-Stars can give peaks, but there is a cited paper and we see them here. So if the stacking is like this, then we have big peaks. If stacking is not how to say it, like with shift, let's say, then we don't have peaks. That's what we see from experiment. And you might ask why. I have no idea. Complicated theory is assumed here, which use diffraction on stars of Davids. Okay, we have a link to this. Shift layers to polarities. X-ray diffraction. Yeah, and that's what's written here about this plot. If they are shifted, then David stars are not paired, and somehow it gives us no peaks. Yeah, and theory that is assumed here is not the theory that I was reading, so I can't comment on much, but these main statements are the following. We get the spacing from these plots, and we learn that they are aligned or not aligned from these plots. Or maybe that's the confirmation, I don't know. Maybe we know that they are not aligned from something else, and also this measurement confirms this. Okay, that's the first part of the results. Second part is presented here. Now we do photoemission spectroscopy in non-commensurate density wave limit. So, okay, maybe it's better to do introduction to this on focus structure tool. So, okay, we already know this from the previous stream, but it's not hard for me to remind you quickly that that's the phase diagram for the tantalum disulfide. And here in this region of pressure and temperature, there is a special, I mean, exactly in this region, there is special configuration, which is, for example, shown here, that Davis stars are arranged symmetrically in clusters, and there is symmetrical regions, there are symmetrical regions of absence of David stars, and that's called non-commensurate density wave. And right now we're speaking about this area. So they did this spectroscopy, in which of course I have no idea how it happens. Yeah, and the results will be discussed below. What we know is that electrons can hop within the David stars. And we need to look at figure 2a. That's the figure 2a. So that's this very clever spectroscopy. Okay, I really tried to understand yesterday this plot. So what does it tell us? That there is a peak of this spectroscopy which corresponds to Star of David, and there are a lot of electrons there in the Star of David. So if we try to understand what's going on with electrons, we can look at like peaks that create this big peak, like feed it to little peaks, and that's how we can understand what happens with electrons inside of a David star cluster. So again, another advanced experimental method is assumed here, but that's the idea that somehow we look at the electrons that are emitted, and we see several peaks, and by them we deduce how many electrons are there in the David star. And positions of peaks are shown also in this plot and also written here. Now there is a comparison of them in the symmetric phase, 1T phase, and LC phase. And as you can see, there are very tiny differences of the peaks, very slightly, like some main peak. Okay, one of the main peaks are shifted, and that's shown here. This blue peak starts slightly to the right. This pink peak starts slightly to the right. That's what we see here. And okay, we also need the annotation, and let's do it a little bit in a clever way. Let's open just another PDF. That's why I actually created this tool to open a lot of things. I mean, to open PDFs faster, so we can put it here and put this here, and also make a window smaller. And now we don't need to scroll much. These are our PDFs that we want to work with. Yeah. So I forgot to tell you the notation that there are A, B, and C types of tantalum atoms. So A is the central atom, B is the one that is close to center, and C is the one that is the farthest away from the center. And here we see also peaks that correspond to all of these atoms, C, B, A, and A is the central one, so A is slightly shifted. B, E, shift. Okay. So the conclusion of this shift is that there is a higher density of states of electrons in the Star of David if there is a shift in between layers. So maybe that's important because later we will be... Yeah, basically that reminds us the main conclusion of the paper, which is not really here. Did I write it? So yeah, so that's connected with the main conclusion of the paper. That's why that's kind of important, that if we have shift, so maybe that's like the most important statement which I will tell you about this paper at all during this stream. So if you have this shift of layers, then they are weakly coupled, then okay, that's I mean, electron orbitals overlap smaller. The overlap is smaller of electronic orbitals. That means that electrons are more inside of the cluster, and that's why there is less hopping in between of them. And that's why there is electron interaction bigger. That's why we have Mott behavior. So that's the main actual conclusion of all this article. And here, let's go back somehow to this second figure. Yeah, which is also actually here, but okay, let's put it like this. So here there is this idea that supports the main conclusion that like this shift of peak is related to higher electron density in the David cluster and the David star cluster, and that's why later we will conclude that electron-electron interaction is bigger. And here I wrote already the question, but I'm too lazy to think about it, that like why exactly this peak corresponds to the higher density of electrons. I don't know. it's not really important to understand it that deep to understand this connection. The main thing is that that's the conclusion out of this photoemission spectroscopy. And you can ask a lot of questions about it, but it's not really important to understand it very, very deep. Okay. Yeah, and the similar statement is here that, I mean, I have already explained that if electrons are more in the center, then layers are less coupled. Okay, let's just go next because nothing is there that I missed. So here they just write that actually there could be other explanations and they are not there because of the reasons that will be here. Okay, I mean, it's not really also important because I don't know all of these proposals. Maybe they have some good ideas in them, but right now I'm just not familiar with them. So for me, it's not really important part of the article. But from theoretical side, it could be really very important. Speech not changed. Okay, so if you want to have S vacancies, then you need to have another peak or a change of another peak, and it's not here. And okay, that's like advanced understanding that in another phase, for some reason, you have extra peak, and it's not changed here. But what is this 2p spectral peak? I don't really understand much. Okay, some shift in spectrum should be also if we have a 2H phase, but it's also not written here. Also, we don't see it here. Maybe it's about this plot 2B. Yeah, exactly about this plot. As you can see from just this letter here. So, okay, from some advanced understanding, we ruled out some theories that are even not explained here, but okay. So the conclusion is that chemical composition is the same. Why? Because this plot is here and it tells us that, okay, there is some advanced idea that I've of course missed as a lot of other ideas because I'm not doing experiments. So it's rather new for me in field of experimental methods. But okay, if we look at this very special plot, then we can deduce that chemical composition is the same. That's what's written here. Okay. Yeah, and just a question reminder for myself later one day maybe to approach this question about chemical composition. So next part, and let's reminder how many parts are left. So we're actually doing it twice faster than the previous stream. Here we have done already 2, and we have 3 other effects and then discussions. So, okay, duality of insulating states, which is the main part of the article. So to understand duality, we need to look at STM and STS, and that's these figures. STM results. Yeah, so if we look at STM, this microscopy, which uses a tip, which goes through material, we can get these well-known plots of densities of electrons. And if we go from one plot, from one state to another, we still have bulbs of electrons. That's why that's what's written here. Yeah, we still see them. Not special. Yeah, so charge density wave is written that it's the same because we associate all these bulbs of electrons as charge density wave. And it's written that it's not special, but we see triangles. So I don't know how to explain it, why here we have more circles and here more triangles. I don't know, but these are the results. Okay, and they also ordered in a plane. That's we also clearly see here. Yeah, and okay, there is 1F figure, 1F. So, okay, that's what I don't understand, and this I wrote already here, that this figure gives us some peaks, and they are related somehow with David stars arranged on the plane. I don't see this connection, but nothing is more written here about it than the statement. Now we will look at the STS, scanning tunnel spectroscopy. That was STM, microscopy. So I think it's the same device, but used in a different way, or a similar device at least. So as was shown in the previous, discussed in the previous streams also, we will measure the current, and these results are here. This is the first phase, this is the second phase. And they changed way bigger. So here in this measurement of the previous section, which I already forgot, I think it was photoemission spectroscopy. So photoemission spectroscopy gave nearly the same results, but now these STS give us very different result. That's what's written here. And that's the description of this plot, that these are the gaps. Yeah, basically these are the numbers that correspond to this plot. And this gap is decreased. That's what is described here. Measured a lot of times. And okay, here this plot was measured a lot of times for some reason. And if you really want, but I'm not the person who wants, but if you really want, you can look at supplementary figure to see how it was measured several times. And what is really interesting is that there is already a theory for this 1T phase. I mean, it's very expected because people know this phase for a long time, but like, it's really interesting that you can say, hey, that's the stacking of the layers, and can you please predict the derivative of current? And I was streaming about one article that did it, but the predictions were not so like exact. There was a big difference between experiment and theoretical function. But here it's written that there is a good theory that predicts something here. If we do not, yeah, okay, but suddenly in another experiment it does not match. I have no idea what this experiment is, but they just mentioned this experiment, that the theory does not match this experiment already. So here it's written that okay, I don't know what is the main idea here. Maybe the spectroscopy, yes, it was measured, it was calculated, and maybe the idea is that we need to take into account layers. So if we have layers, and if we do the calculations for layers, then we will have a better prediction of the current. Now there is definition of TC phase. Okay, and we need to look at the image, which will be maybe later. Where is this? Okay, that's related to this statement. Yeah, okay, so we will see image for this TC phase later. It's about the stacking, like how these layers, what these layers look like. But this is not an important sentence, it's just a comment to the previous sentence that for some different stacking there is not so okay, no, maybe there is still a good prediction for another stacking because they were simulated and measured, so maybe everything is really fine. Have some messages. Okay, yeah, I did a not so high quality summary here. So, okay, maybe my conclusion is that this STS was obtained from layer interaction, and or maybe layer non-interaction. That's why it supports the idea of interlayer decoupling. Okay, I'll think about it later. Maybe that's my conclusion, that there was calculation of this STS spectra, and it was because layers decouple. And that's just a comment for which configuration it was obtained. Should be for bigger gap. Yeah, and obvious statement is that if we have a bigger gap in this phase, then there should be some reason. Maybe this band-insulating mechanism, which is also maybe will be calculated in this page, in this paper, and maybe exactly right now in this DFT calculation we will be presented with these results. Okay, so now we will do this ARPES, and let's open this image here because that's more comfortable way. So we will do the ARPES measurement. So we'll shine photons and see how many electrons go at some energies. So it's a very standard experimental method for this material. And they reproduce the established results, and they did it for, then also they did this ARPES for different phases, and you can see here there the different results. That's for LC phase, that's for the 1T phase. So maybe let's remind, because someone might forgot, that here that's the definition of LC phase, where there is a shift, and 1T phase is the symmetric phase without any special shift. So ARPES was obtained. And what we can see is that if we decrease the temperature, then gap increases. So there is a conduction band somewhere there at the top, which is not measured, at least here in this experiment. I don't know if it really in general can be measured by ARPES or no. Some plots show something here, but some of them don't. But what is written here is that if we look to this gap and to this gap, then we can see that this gap increases. That's what's written here. And I don't know why ARPES is so blurred about. Yeah, okay, let's write it. Yeah, okay, I don't know why it is so blurred, but this is the results that were given. And also, okay, what is really important about ARPES, that to get these results, we have these results. So as far as I understand, this is the scan over the vertical line. So if we go like this, so at 187 Kelvin, so like this, then we can have peak here at minus 0.6. Then it goes to minus 0.2. And also there are different energies. So no, I'm not expert of this thing. I just know that they are somehow connected. I tried to understand once how they're connected, and I'm not sure about really the correct answer. Because here we see the main peak is around minus 0.2, but here the peak is around, yeah, maybe it's just about this region of the energy. Yeah, so somehow these plots are connected, but I haven't understood fully how. But it's not really that important. This is just a comment to this plot. And this plot will be compared later with the calculation. Okay, that's the introduction to that plot that I discussed. This plot, I mean, at least tried to discuss. And there are comments about this 3G plot. That's exactly this one. So peak goes here and then goes here and then goes to the right and then goes to the left again. And these results were obtained before in some paper, in this paper, but it's not written what exactly is the meaning of this. Okay, but if you want, you can see something similar in this paper. Yeah, and at 20 Kelvin, you can see that these plots are nearly the same. That's what's written here. So how structures. Okay, maybe that's here there is an important conclusion, but I am just have some messages. So I don't know why it is so, but that's an important conclusion that layer structure is not the reason for Mott phase. So maybe the reason is that, look, we have the Mott phase at low temperature, and look, that's the layer structure, that's the non-layer structure, and I mean, okay, both of them are layered. I mean that this is with shift structure, this is without shift. So if we change the shift, then there should be a different spectra if layered interaction is important, but no, we don't see a big change. That's what written here, I guess. Yeah. Okay, and here there is a reference to another paper about another sliding, but on a surface. I don't know what it is. Yeah, but I will write it in the red, like this more question, not the comment. So what is this sliding that is announced here that may explain this? Okay, just write. Yeah, I was thinking about it, why the results are different, because still we see a very big difference. I have no idea, but I just want to have a red question here about it, not to forget about it. Okay, so now we will discuss the DFT calculations, and let's put this image here. So they were done, these well-known numerical methods of calculation condensed matter. To get it done, we need to know the configuration of atoms, and for this we have the X-ray diffraction. With this diffraction we get the positions of atoms, and it was done also before, so we have good citations for previous calculations, and it's really a thing that I would like to look one day, definitely. What is meant by disordered David star stacking configuration? I have no idea. Okay, let me write it here. Okay. So introduction to DFT. So we got the input from the experiment which was discussed before. Let's forget about this sentence because it's a strange one. I don't think that there is a disordered stacking configuration. There is some shift as we discussed before. So I don't know what they mean actually. But okay, I wrote this question already. And now that's the introduction to these plots. So we have a different spectra and we have a different shift. So this is the stacking. So that's the important figure for this notation. So so stacking A, I guess, it's when the central atom corresponds to the central atom. Stacking B should correspond to like central atom of the David star to the B atom of this David star. And stacking C is when the third, farthest atom which is farthest away is in coincidence with the central atom of the next layer. Yeah, so let's see what will be for these two configurations. And here, these are the results. That what if we do just the Tate-Biden approach? Oh no, maybe not Tate-Biden approach, but Mott-Hubbard approach, I guess. Okay, actually, it's a good question. Okay, maybe even for not Mott-Hubbard approach, maybe DFT has their own formulas, which I don't know right now. But yeah. So that's the introduction of the notation. That this is index S, which means shift, and AC, it means like what is shown here, A. Then C atoms corresponds to A, and again A corresponds to A. So that's the periodic stacking. And we don't have TB because yeah, we just don't think about this more complicated configuration. Okay. So what happens here? Okay, sorry, we need to look at these two images. So here we have an insulating state, here we have a metallic state. And that's for the shifted configuration, that's for not shifted configuration. But we say that actually we don't like this, it's not really true, so we need to add Hubbard term. Okay, so that's what's written here, that you need to really know well DFT because you can do this and get some results, but no, you need to add also some extra parameter. That's what's written here. And the reason is that you just don't like the results. So if you don't like the results, you need to change the method. And if you don't know that these results are bad, then I don't know what to do. So they recalculated it more carefully and got this plot and also this plot. And one of the conclusions is that, hey, before we didn't have this U term. So even without U term, there was a gap for non-shifted configuration. And that means that U term does not give us the energy gap, because even without it, there was a gap. And also they got the result that actually just shift gives the result, the change of the spectra. I'm not sure why. Okay, maybe because there was this figure for supplementary information. So if you change the vertical distance, then you don't see a big change of spectra. That's how I guess what happens here. But if you increase the shift, then you have a bigger change of the spectrum. And another thing is that like here you have actually like a lot of layers, like 40 layers as far as I understand, but it's hard to do calculations in 40 layers, so they did it in less layers, but increased the shift comparing to the real one that was obtained from some diffraction, or maybe from some microscopy. And they argued in methods more about it, so maybe we will look in the methods section more. Right now, I just am not sure. Yeah, I'm not sure what is the argument that they can increase shift but decrease number of layers, but that's an important statement in scope of their calculations. Okay, so these are the results in their calculations, and these are the results with the spectral functions. So each band has its own number of electrons that can sit there, and this is shown here also. And this is the thing that we will discuss slightly later. Okay, let's put this image here and go further. Okay, maybe that's what will be discussed right now. So also they calculated density of states. Yeah. And look, like there is first phase, second phase, and what is the density of states on the Fermi surface. And look, there is a gap here and there is a gap here. But to get the gap in the second configuration, you need to use another computational method. That's what's written here. Okay, they can't reproduce experimental results. I think to see. Okay, yeah. Nothing is important. I mean, that's my just understanding that still they can't reproduce experimental results, but let's just check. I mean, and just write it as the question here. Because I feel that no one has ever reproduced it, but I need to check it. Here it's written that trends is are consistent from experiment and from theory. Okay, so now the second paragraph. Okay, so here we see these two spectra. This is for non-shifted configuration. This is for shifted configuration. The bands here are more flat. As you can see here and here, they are more flat. But yeah, maybe this band is also flatter, but it's harder to see this. But that's what's written here. Yes. Okay, so I have already asked this question that actually ARPA's result, which is, as a reminder, this result. So this result is not actually the same as this result, but the general trend is that it's more, both of them are flatter in this state of the shifted configuration. That's what's written here. Trends and similar. So gamma A I'm confused about this sentence. Okay, I don't. That's also a question here that I did not understand this sentence, but in other direction, trends are similar. So maybe if you use this direction, gamma A, and if you use this direction, then yeah. So it should be also more flat. It should the bands should be more flat, but there are extra bands, and that's why I'm not sure about this sentence. Like in this direction, something happens which they don't comment. And again, there is repetition that the trend is consistent with ARPS. And just my understanding is that why this is not very looking like this is just because ARPS gives a lot of errors. But I have already written the question why there are more like uncertainty in the bands in this state compared to this state. I have no idea, but okay. These are these plots, and that's the end of this paragraph of discussion of the bands 3H. Okay, maybe I need to think more about this phase. As photon dependence. Okay, that's this phase. We need to find the peak on minus 0.2, and it has less photon energy dependence. So if we increase the peak, so yeah, that's what we see here, but I just need to understand how this is connected with the previous sentence. Yeah, it's consistent, but yeah, why this peak, if it doesn't shift much, why is it connected with the reduced band dispersion? I don't know. I'll write the question here. Also, I wasn't thinking about this yet, unfortunately. But the connection is also not written. We just see a statement which is illustrated in this plot. Okay, now let's discuss the same thing for several layers, I guess. That's the hard part. So, okay, that's just my guess that, like, if you increase layers, then you have some DFT calculation. They can do DFT calculations also for this, and they give the Mott insulating states, and this corresponds to the flatten to bands that are more flat. Okay, maybe it's better to not to be so fast here and a little bit think more. Oh, I have a new message from someone. Okay, it's not important message. So that's definitely about this plot, because these are these directions. So around Fermi energy, it's written that bands are flatter. Okay, so that's my best understanding of what's written here, I can tell you something better, that if we look at this image, then we have flatter bands near Fermi level, and that corresponds to the Mott insulating state. But unfortunately, I don't really understand this, and I need to write a question here about it, that I understand it worse than I should. But that's exactly what's written here. I just don't understand why you have this statement. Also, actually, we don't see a gap here. Yeah, okay, that's a good question. Yeah, okay. Let's just skip this sentence. Okay, so suddenly we have a conclusion that this phase should be three-dimensional band insulator, not a Mott insulator. And how we can conclude this from the measurement? Oh, okay, we can't conclude it from anything. We just have this citation, and nothing is more written here. And we can't reproduce full experimental data. That's what's written here. But they guess that maybe more realistic stacking will help us to get the what? Metal bands. Yeah, maybe we will get these bands if we... Maybe the stacking wasn't... Yeah. Yeah, maybe the stacking wasn't exactly as was inputted to the calculation. That could be the reason for the difference between this and experiment. But this looks very strange actually right now after discussing this, because actually we don't see this gap, but we should see the gap. So is it correct or not? Yeah, that's the question about these results. And right now we're coming to the last part of this results. Now it's the easiest part of all other parts. So what is the effect of electron transport? I mean, the theory which is assumed is rather complicated, but we need to understand on the statements that, okay, we will measure mobility and carrier concentration. What is the mobility? Actually, carrier concentration, okay, like mobility is how fast electrons are moving. And what is the carrier concentration is that how much electrons do we have. And we don't need to know much except the formulas that are written here. And of course, there is a complicated theory that is assumed, but we don't need to understand it to understand the results. So this is the formula for the concentration of electrons, and that's for mobility. So we need to measure some Hall resistivity and yeah, that's the Hall resistivity and Hall coefficient. What are they? I haven't revised, so I can't tell you, but nevertheless, we just know these main formulas. So we can see that the concentration is different. So sometimes there are more electrons and sometimes there are more holes. And some results are already known about these materials. And like this change of this concentration is the signature of this translation of these two states that are already known. And I forgot to write here my comment about this sentence, but there's also a gap opening, so maybe they're consistent one with another. So if we have a phase transition, then simultaneously a gap opens, and we have this distribution of electrons, which is different. So somehow really complicated, in a complicated way, people connect this to effects one with another, the phase transition and the change of the concentration mobility. Yeah, okay, so now we maybe need to look closer on these plots, and if we look at the, maybe first of all, mobility, then here in this phase, in this stacking, the mobility is way smaller than in the symmetric stacking 1T phase. That's what's written here, but at the opposite, n is way bigger at this phase, and it's obvious because like we have this formula, so we have the whole coefficient, and as you can see here, the n is dependent only on this because E is the electronic charge, I guess it's a constant. So if n is bigger than mu, should be smaller, and that's also what we see here. Yeah. And they relate this behavior to the gap. Why is it related to the gap? It's not written, and also the connection between, I mean, the derivation of this behavior is also not present here. So just it's a left question. And so, okay, okay, so maybe here just a summary of what happened before. Okay, now we will discuss these two plots. There is also a resistivity, but resistivity can be in different directions. So first of all, we do normalization because there are a lot of other effects and I don't know anything about them. The only thing that I do know is that if we take them into account, it will be a very big activity. So that's why we just do this normalization. That's written in this sentence. What's written here? So here we need to look at this direction as far as no, maybe to this direction. Okay. Okay, sorry. Okay, 5C. That's this exactly image. So we should look exactly at this direction. And if we look at these temperatures, then these are the same temperatures, same values of resistivity for both phases. The thing is that they have this phase transition at different temperatures. Actually, it's a good question, which I wasn't thinking about. Yeah, we see that this phase transition is on different temperatures, but I haven't ever asked myself why is it so. But okay, the idea is that these values are constant and they are the same. Yes, and that's written here. Then at these low temperatures, then resistivity is already not the same. Yes, I'm just curious. Yeah, it's interesting actually. I'm noticing it on the first time that there is a red thing here. So if you maybe cool or warm, then these phases have similar resistivity, but if you do opposite thing, then these phases have a different resistivity. And okay, that's, I don't know how to explain this. Maybe that's a bug in their plot. Okay, I'll just write this question. That's a very strange question. Yeah, okay. But nevertheless, that's the description of this plot. Now, what if we measure resistivity in another direction? Then we will need to look at this plot. And right now, there is already a difference somewhere. So I tried actually to understand this statements here, and I can't say that I succeeded because they are not clearly written. But idea is that there is maybe this jump which is bigger than here, which is very strange, right? But okay, that's the maximum information that's written here. Yeah, that's what just written here, that this jump is bigger than what we have seen before. Okay, these are ideas why this happens, then that this jump is here and this jump is here. And okay, these are just ideas that maybe if we have less coupling, then electrons are more localized, so they have bigger effective mass, so the resistivity is bigger. Sounds like a great idea, but we also want to have some formulas, and no formulas are written here. That's why I have this question. Okay, now the section of discussion, and maybe that will be an easy section. So, so in this phase, B layers dimerize. What we mean by dimerization is that there is a strong interlayer interaction. As you can see, I have discussed all these papers, but I still don't see the real reason why they dimerize. Maybe let me think why they can't dimerize, why they should dimerize based on everything. No, I thought about it for, let's say, 10 seconds, and I have not understood why they dimerize. Well, maybe, okay, we can say that we are reproducing these results if we're taking into account the coupling between two layers, and that's the one argument. Second argument is here that resistivity is okay, maybe I said wrong. No, because what happens? So the problem here is that this argument is valid for both phases. I mean, yeah, like both stacking configurations, and yeah, okay, maybe I'm not sure about what was written here, because I thought that bigger mass is because electrons are more localized and Davis star clusters, but we see that if we change the the stacking, then localization is changed, as we know from the previous discussion, but the maximum value of resistivity is still basically the same. And the thing is that the only what we see here is that the resistivity has a jump at different temperature. Yeah, and that is not explained here. It's explained about the ideas that here we have a bigger gap than here, and that's my explanation, that it's related to the what? Okay, I'll write it here. To the increase of mass. Okay. Okay. Okay, that's my attempt to understand why they are dimerized. My version is that because some advanced theory is assumed in DFT, and here they take into account the interaction between the layers, and if interaction is bigger, then reproduction of results of spectrum is better. That's just my understanding. As you can see here, I don't clearly understand this conclusion. Okay, I made a mistake here. It should be written they do not dimerize in 1T phase, and that's obvious because we have this shift, so Davis stars overlap less, so they interact less. And that's also connected with this obvious statement that if electrons are more localized, then they stronger interact within each other and not with other electrons. It was actually interesting that in the what? I have a new comment on YouTube, but I will reply later. Is the interaction between several students the one place Yeah, okay. That's an interesting question, because before I had an article about the electron configurational states, and they say like, hey, we have just one layer and there are interaction of electrons, so let's just focus on this. And here they're not writing anything about it, so that's the question about it. How did they take into account this? But they say like, we do DFT, so I guess maybe yes, maybe they take into account literally everything which is possible in scope of their limit of applicability of DFT, which will be discussed in the section of methods soon. Okay, so that's what's written here. And okay, if electrons are localized, then U increases, yes. And if U increases, then we don't have as much hopping in between of layers. That's also obvious. Yeah. And the analyzed transition of layers. Okay, so now there are some promises. Maybe you can create some new devices with this knowledge, but maybe no. And it's not clear what they mean here in the last sentence, the one before last sentence. And also maybe they can do something with ferroelectricity, because it was cited already before that this work was done. And maybe you can do something more there. That's all what's written, and we have now the methods section. I wanted to show you how much have we done. We have covered all like all this, and we have just basically one page of the methods, which will be fast because it's rather technical supplementary information. But okay, so how do we prepare samples? And that's really interesting thing from experimental point of view, because I don't know, it feels that it's a really hard process. So that's just my fast summary. So they use chemical vapor transport somehow. Yeah, and that will be the chemical vapor transport. So first you mix these two elements, then you put them to the vacuum, then you heat, then you wait, then you cool fast. Then you use iodine because this is still air, so you need to transport it somehow and to grow a structure. So for some reason iodine is used, because these are clever people who are doing this experiment and they know that exactly this material will work. I mean, this element will work. Then you heat and cool, and also do it at the different sides of the tube which has this gas, and then you cool fast at the maybe cold part of the tube. Then you put it to the vacuum. And okay, so the real good summary of this part should be the one that will tell you why exactly do they have exactly this shift and how they can create this material. And I tried to understand it maybe for 20 minutes in my life, or maybe even more, just this part. But I didn't understand. They just write that LC crystals are obtained after cooling nature. Why is it so? It's a very big mystery. I have no idea, but it's not written here. We just have this strange recipe. Then you have also typical advice to store it in vacuum. I mean, part of recipe, and also cut into pieces before measurement, which is not complicated parts of the process, but I can't extract, unfortunately, why exactly this way is used for LC phase. Okay, now the second thing is electron microscopy. The scope of this method, we are given just the title and some parameters of the device which was used. X-ray diffraction. It's about that figure. Let's see them, 1C and 1H. Yeah, these complicated figures. So we shine some photons and get some reflected photons and measure reflected photons. So this is the name of this facility where this experiment was conducted. And these are parameters of the wavelength, angle, and there is a main equation of X-ray diffraction, but again, you need to read a paper about it to understand really what happens and how this data is giving us something useful. Okay, and there is the comment about how did they get a parameter that is used. So it also falls in scope of all understanding of X-ray diffraction, and it's not really main point on the image somehow of the article. Somehow they did it, but okay. And there was another experiment of X-ray diffraction, and I guess that's maybe this plot which was obtained by this X-ray diffraction. And it was done on the same material. Yeah, you can see it by this labels on the plot, the temperature here and here. Okay, and that's the X-ray diffraction. Just a few comments about the experimental setup. Now this ARPES, this thing that gave us this. So this name of a place is here. It's in China. So they cut the material, put them into vacuum. They measured the spectra, and somehow they got information about the photon energies by some another measurement. And they also used the method for fitting. So I'm not expert in this ARPS, so I don't know what did they fit. Maybe this peaks somewhere. Okay. Okay, no, unfortunately, it's just about photon emission spectroscopy, so it's everything what I told you, it's about PS, not ARPS, and now the same is about ARPS, that's the name of a place. And seems that it's the same laboratory, but another beamline. And that's the preparation of the material, and also for some reason they use very low pressure chamber. And also they got Fermi energy somehow with some gold foil. So it's not really informative for me, and I'm not expert in ARPS. So here we have just some comments about the ARPS setup. Now we go to the STM and STS, and this is the plot which is better to have opened when we have a discussion of STM and STS. So again, we have name of the laboratory, we have the experimental details, constant current mode, something. Okay, calibration of, again, another material, and the temperature, and yeah, and the pressure. So these are just features of the experiment, so we just need to believe that these people know what they did, and exactly these parameters are the best parameters ever, and that's what's written here. Okay, now the last plot is about the mobility, so these are transport measurements. Okay, and that's the name of the device. They changed the temperature because we need to have a movement along the horizontal axis, which corresponds to temperature. And yes, they were measured in plane and out of plane. They did some fitting to get the whole resistivity, and there are some errors, but they're small. That's what's written about these measurements. If you want to know more, you can read about these names, PPMS, quantum design. Maybe there are some cited papers about it. I'm not sure. Okay, now the last part of the methods, DFT calculations. So that's the name of a package. The methods, name of methods which are used in scope of DFT, and that's the that's the papers that I downloaded after reading this. Maybe later I will read them. They're very cited. They're very well known. What's written here is that they have Coulomb repulsion parameter, and I have already tried to understand how this parameter is related to the parameter. Let's open another focus structure tool if it opens. Yeah, it should open. So you might remember from my previous stream that there was this Hubbard model, and in Hubbard model there was another U parameter. And there is a purely different value of this U parameter, and here that's the value for Coulomb repulsion parameter, but this is DFT, so some another formula is assumed, and my version, I mean, I'm assured that that's the correct answer, that this is just two different parameters, but I need to understand deeper DFT calculations because I don't know what exactly this U means actually. And again, we have now name of the orbitals, and that's actually the value of that U parameter that I just showed you. So as you can see, it's a very different one. So I'll think about it later. So we have a computational parameter written here. And also there was another famous method for taking into account another effect, but I don't know what is the... Why do we need to take van der Waal interaction effect into account? But these people definitely know, and that's the name of this method. Then information about the grid, then the information about the code. So maybe they use this package for something to get the first bands, and then the code was used for unfolding. But for me, I'm not expert, so I know that there are these two codes. So some clever people use them in a clever way, and that's how they got the results. That's how I understand what's written here. And we have just one last page of the text. Okay, that's the DFT. I don't know why, but suddenly we switched to first principle calculations. So now we're describing the 1T phase. Yeah, we maybe need to open this image here because it explains what we mean by this TEA and TC. So here we have just extra comments that there are these vectors, and that's rather well-known notation, but it's not explained here, so I can't tell you more. We just have these vectors which were used to do this first principle calculations. And it was also done before, so luckily we have these citations. And that's the comment about this plot, that we have this stacking geometry. And yeah, if we have shift, we have this delta here. That's illustrated here on this plot. And now there is a important discussion of why did they use a bigger shift compared to the real experiment, because they have also less layers, and they argue that they can do it. So not to calculate 40 layers, they calculate 4 layers, but have and write a bigger shift. Yeah, I think that that's the bigger shift. I'm a little bit not sure, but I think it's so. So they write that they can't do calculation of a lot of layers, like not 1,500 atoms, but just 4 layers, which maybe has way less. Definitely should has 100 less. No, 10 times less atoms. So instead of 40 layers, they have 4 layers. So that's why I think that there should be 10 times less atoms. And they will use bigger shift. I actually missed the argument why this is really a great idea, but okay, that's what they do. And they check different shifts also. Okay, then there is a very unclear sentence, but maybe they check that they can reproduce some results which were obtained before. I don't think that's an important sentence. And they also check what if they have 8 layers and a different shift, and maybe they concluded that for 8 layers it's still the same approximately. Okay, if you want to understand the dependence on the shift, you can look at supplementary figure. And also they have here a criterion for the proper shift as the one where the gap closes, but I don't understand this criterion, and it's not explained here, and I asked GPT, he didn't tell me much useful. I still do not understand it. And also there is the second parameter as the interlayer distance, and it's also an important parameter, but they ruled out the influence from it. And maybe here also there is a reason about it. I didn't check exactly this detail. Okay, so that's again the argument about their distance, the shift, so it should close the gap for some reason. So as you can see, nothing is very well explained here, but if I really want, I can see supplementary figures, and unfortunately maybe they don't cite much. Okay, maybe I can read the cited papers and maybe it will be enough to understand this. Okay, so another sentence is that actually if you use the GGA plus U method, then you have a big dependence on U value. And maybe we need to be very sure that this value is the correct one, but we don't have any information about this U value except the value. But we have the citation, so if you want really to understand why U is so, then this is a good citation to do it. And there is the last sentence about the alternative, that actually there is GOU method, and maybe you can try to do it and get some better results. So that's the end of the paper, and I have my discussion. Fortunately, I did not recompile it. I have already changed this LaTeX bug. I have some little discussion with GPT, which is not worth of discussing right now. So let's conclude what we have learned today during whole this time. So we went through this article. So yeah, maybe I can try to again extract something more useful, and you can compare this attempt with the attempt in the beginning of the stream. So a lot of experiments were done, a lot of measured methods were discussed, and the idea is that they use this shift of the stacking in order to figure out what is the influence of this stacking. And as you can see from the theoretical description, even with and without stacking, there is the band gap. So stacking is not important for the gap. We also saw a lot of experiments. So that's why, like you see, I wasn't assured about the key takeaway from the article. Right now I have streamed all this article and I'm not sure what to tell you as the main takeaway. So these are the results, these are the ideas. I mean, this is the setup. This is the property of what photoemission spectroscopy, scanning tunnel microscopy. So the gap, it's still there, and RPES gives similar plots, but plots are still slightly different. Actually, here you can see that it's way more different, and they don't comment much about it. Oh, sorry. They just give us other plots, and okay, that's the theoretical calculation, and it's not actually consistent with the experiment, right? We have here these two hills. Okay, here it's slightly consistent, but here it's not that consistent. Where is it? Yeah, okay, so here we don't see such a big like lowering of the band of the derivative of a current, but to some extent it reduces the results. So yeah, what is the conclusion? These are the experimental results. These are the results of their calculations. I mean, this is the results of their calculations. These are different experimental results. So you can compare the stacking and the effect of them. And basically that's the main article. So it's, for me, not clear what to do with this theory and what is the really important conclusion. And how should we understand this material in a different way after this work. But definitely I missed many things, so maybe later we'll return to this. So basically that's the article. So I like this format where I don't read in front of, like during the stream sentences, but mostly read my revision of this. So not so many complicated things happened, just different experiments. This first type of experiment, second type, third type, fourth type, fifth type, and sixth type. And also the theoretical calculations, which were done using the cited papers. Okay, and this, and this. No, yeah, like this, yeah. Okay, so that's the end of the stream. So we have discussed this paper and learned a lot of things during the stream. Again, if not such stream, then I would not be that motivated to really think that deep, because it takes a lot of energy, and when I do the stream, I feel that energy is flowing, it's not staying somewhere in this room where I'm sitting. And that was a very hard paper because it was like about experiments, and I wasn't doing experiments, so I learned really a lot of new things. But the goal was to learn what to do next as part of my research, and this paper didn't give me answers. It gave me just a broader overview of what happens with experiments. So thank you, a lot of viewers who were joining and then dropping out in, let's say, 2-3 minutes. It still was nice to see so many of them during the stream. And if you have some questions about this article, you can write them in the comments, because maybe it will be already several months since the stream was created. So maybe after that time, I will give you more like advanced answers on these questions. So thank you for the view. Bye-bye.